Okay, so there were two more questions. One was, when should everything be turned in? So I'll answer that one. When should everything be turned in? So finals end on the 20th, and I'm almost positive my grades are due on either noon or midnight on the 22nd, so just be sure everything's, turned in by the 20th or 21st. The other thing I mentioned, there's two, if you don't finish everything and you don't communicate with me about it properly, I'll give you an incomplete if your grade is not sufficient to pass. If you did say, hey, I've got something came up, I need more time to finish, I'll give you an N, and then whenever you do finish, that whatever grade you get will be your grade. If you get an incomplete in a course, your transcript will actually say BI, meaning that you had an incomplete, but then you did finish. With an N, there's no footnote. So that's finals, and then the other question was about the syllabus. So I will, and sometimes there's a discrepancy between what it says in the syllabus, and so if the exams, let's just say the exam total equals 50%, is that right? Is that what it says? Yeah. I might even have it up right here.
I have the percentages and how it breaks down.
Okay. Yeah, so there are seven exams, including the final. That number should say 6. So let's just go through an example. I showed you this, and I can even just do it for you in Excel. This is how I would run through this in Excel. Yeah, so if we just had 1, 2, 3, 4, 5, 6, and then here's your final. And let's just
Extra ones.
Thanks. 5, 6, final. Delete. So let's say we have 0.9, 0.85, 0.7, 0.65, 0.9, 0.95. Let's just say you aced the final. What I would do over here, I would just say this equals the sum of these guys. So that's 4.5. And let's see, so that's the max you could get. Then there's the other guys too. So if I did it this way, let's just say this is going to be perfect. If I had 1, 1, 1, 1, 1, 1, let's just take this guy, move it over here. There's the sum. Let's see if that actually works. There's 6. So then to get this, so then I just need to get this to be 50%. So this is going to equal, so this is going to be percent. Six is going to be 50%. Equals. I have to do this by hand really quick here. So I know that. So 6 is to 0.5 as your grade X is to is it that simple? 6 is to 0.5. So I need 6 to map to 50%, And then I need your grade also to map to 50%. Is this right? 0.5x equals 3. X equals 6, is that? Yeah.
Well, doesn't it account for like 50% of our total?
Yeah, it does, but I'm just struggling with the algebra at the moment. I just need to get 5 to turn into 50%. So 6. Let's see. Equals that by 12. Yeah, I guess it's just that simple. Copy. Paste. Just, figure out an appropriate formula. So if you had a perfect sum total, you'd have 6 points total. It could also be 60. It really doesn't matter. I mean, the point is at the end, if you had 6 points, or in our case 60, that's going to map to 50%. And if you had 4.95 out of 6, that's going to map to 41%.
That makes sense.
Yeah, that's all it is. So,
So then technically it would be like an 82%.
yeah.
Yeah.
Yeah, but then there's the summaries and the problem sets to get weighed into. So I think as long as these add up to 100, so there's 50, there's 75, there's 90, and there's 100. So yeah. And on the participation, it's just, did you go in and comment on your classmates' summaries? Did you email me? Did you say, hey, I'm going to be gone from class, et cetera? Since it's an online course, well, since it's a hybrid course, just go in and say, hey, you were in the face-to-face section, why didn't I ever see you in class? Or, so.
Yeah, question.
Yeah.
I'm looking at summary 5 here, and you give us 2 options.
Oh, yeah.
The first option is summarize the major points from the article below.
Yeah.
By Dr. Layton. There's no link for the
Oh.
article below.
Okay.
And I want to do option 1 because option 2 sounded way harder.
Let me get you, okay, I'm glad you asked. Let's go ahead and do that. This one?
Yeah.
That guy didn't work?
Yeah, instructions for summary 5.
Yeah.
At the top.
Oh,
Yeah,
sorry.
I
Here's
thought
the
it was
paper.
on the same page as on
Yeah.
the previous page. Okay,
Okay.
never mind, it's there.
Okay.
All right.
Sorry if that wasn't clear,
No,
yeah.
that's all good.
Okay. Yeah. Well, I guess, since you brought it up, let's just take a quick look here.
Number 1.
So, yeah, number 1 isn't a cakewalk either.
Yeah.
But for example, though, in option 2, this Gordon Butte pumped hydro plant would be a really good one. And then there've been a lot of community solar projects going in. Not a whole lot of geothermal in Montana, but if you want to take the geothermal route, someone you might look up is Susan Petty. She's done a lot of geothermal.
I can understand Yellowstone National Park, but definitely a good hotbed.
Pretty good thermal resources in Yellowstone, absolutely, yeah. Susan Petty's actually written up a proposal to do geothermal at Colstrip, so that's been on the.
Let's say it, name sounds familiar.
Yeah. She and Nikki Fear both won this neat C3P award here recently, so you might look that up.
So how far does I don't know if you know or not, but how far does geothermal go down?
It depends how close the thermal resource is.
10,000 feet down, you're looking at like 260 degrees.
Yeah, I mean, or shoot, just walk, stick your finger in the water at Yellowstone and it's boiling. I mean, there it is. Yeah, yeah. And there are two types of geothermal. If you take 102, we'll get into them. There's the high enthalpy and low enthalpy. And if you're high enthalpy, you can make electricity. Low, you're just kind of doing district heating. But yeah.
Okay, interesting. That's the 2 class, Energy 2, you said?
102, yeah, 102. If you notice, I mean, this 101 just covers almost completely conventional, non-renewable energy sources, but 102 is only renewables.
Cool.
Yeah.
And that's offered this spring.
In the spring, Energy 102, and I'm going to be teaching that on main campus. Yeah, yeah. So that's one, and then since it came up, and this actually is relevant to the penalties. The penalties chapter 13, penalties. But let me just walk you through this one a little bit. This paper came out. I've got two separate papers. One came out in December of 2014, and the other one came out in January of 2016. This paper was actually inspired by. Let me just see if I can do Richard Fine, Shannon, and Carnot quote. I might even have it in the paper here, but here, yeah, let's see if we can find it. Yeah, okay, so this one quote, this one quote kind of inspired the paper. So Richard Feynman was a Nobel laureate. He was one of the youngest physicists to work on the Manhattan Project, and he's kind of a popular figure as well. So, yeah, this is the quote. In fact, the science of thermodynamics began with an analysis by the great engineer Sadi Carnot of the problem of how to build the best and most efficient engine. So we did Carnot efficiency, if you remember, in chapter 4 or 6, whatever it was. And this constitutes one of the few, so here's also classic Feynman. He's both praising and he's like praising Carnot and dissing all engineers in the same breath. One of the few famous cases in which engineering has contributed to fundamental physical theory. Another example that comes to mind is the more recent analysis of information theory by Claude Shannon. Shannon was out of Bell Labs. I think he was at MIT for a while, then he was also at University of Michigan. There's a bust of him there at the electrical engineering building. These analyses, incidentally, turn out to be closely related. And so what I was attempting to do in this paper is show how those two things just now, Feynman's been dead since 1985. Carnot lived in the 1850s, and Shannon was in the 1940s. A lot of his papers were classified. But Shannon's kind of ushered in the digital age. He was, working on these 7th-order differential equations, because that's how all the vacuum tube computers used to work, and said, hey, let's just go digital. I think, if I'm not mistaken, coined the word bit. But here's the paper. So that's where, yeah. And I've got the second paper actually calls out Shannon and Carnot in the title. But there's Clausius. You mentioned Carnot. We know what Carnot efficiency is. It means that in order, somewhat ironically, in order for something to be more efficient, it has to get hotter. There it is. And this is entropy. And let me just show you. I know we talked about it briefly, but entropy it's S, it's denoted by the word S. And typically you think of a change in entropy. And what that is it's the change in heat of something divided by its temperature. So every time, and the way to look at that is if you have engine and you've got cool gas coming in, and then of course when it's burned, you've got the hot gas coming out. You have, and then you also have some ambient temperature. It's just the temperature of the atmosphere, AMB, ambient temperature. So when you go from cold to hot, you get some change in heat, right? So the gases coming out of the engine are hotter than they were going in. Same thing at any plant. Same thing at that cooling tower in China where 60 people just died when the scaffolding collapsed, right? They're actually trying to build one of these. Giant cooling tower, because that's how thermal engines work. So, and every time this thing cycles, every time the engine rolls over, you get another increase in entropy. The universe just became more disordered. You had octane sitting there and oxygen, and now you've got all, CO, CO2, SOx, NOx, all this other stuff coming out. So that's entropy in a nutshell, going from an ordered state to a disordered state. The universe is doing that all the time, like it or not. It's just the second law. But my point, and I think I wrote this, anthropogenic, human, entropy, we know what that is, acceleration. It means that, every time we do something, you're not going to slow entropy down. You're only going to speed it up. So the question is, how much are you going to speed it up? It's the same thing as time travel. You can sort of slow time down by traveling quickly, but you're never going to go backwards. So you can only slow it down a little. So with entropy, we can only speed it up, or sit around and do nothing and maybe just keep it the same. So that's the okay. So that's entropy, and then what I tried to do in the paper is come in, and so you can look and you can see that there's the sun is generating entropy. The little dot there, this is all this means. And so here's what the dot means. So here's time, and here's entropy. And as I said, entropy can, it can go up slowly. It can go up, at a medium rate, or it can go up quickly. And the point is, it can go up at various places at various times as well. In the same way that you can have, a change in temperature, like it's going to get hotter more quickly where the sun just came up versus where like the sun's already been shining for a long time, and it's going to get colder more quickly where the sun just went down, et cetera. So each of these curves can be for a particular region in space. Now, the way to think about it is here's a change in time, and here's a change in entropy. But if I just zoom in on a little tiny point, the slope is just S dot. So S dot equals the slope of entropy curve. So right here, I did it for the sun and said that the sun is, it's burning pretty hot. So 10 to the 22nd watts per Kelvin, and that's just the background temperature of the universe. So that the sun is creating its own entropy. And then I come back down here and say, well, the Earth is doing the same thing. The universe is doing the same thing. So each one of these little rates here is just watts per Kelvin. So watts per Kelvin. Why is it watts per Kelvin? Well, because entropy is energy per Kelvin. Or I should do it this way. energy per temperature, which is measured in joules per Kelvin. And then when we look at the change, let's just I'll sneak the change in right here. So the change in entropy per unit time equals the change in the joules per Kelvin per unit time. And the change in joules per unit time is just watts. Because we know that watts are joules per second. So that's why the unit's on S dot. So, and this should make a lot of sense based on how much time we spent discussing power, because power is how quickly you use energy. So it's the slope of that line. If I'm using it really quickly, there it is. If I'm using it slower, there it is. If I'm using it, really slowly, there it is, even slower.
On like a smaller scale,
Yeah.
could you like kind of show this like in fact of like if you take like a jug of water, like a warm jug of water, and
Yeah.
stick it in the fridge, like that's gonna cool off quicker obviously than if you stick like a cool jug of water.
Sure. Yeah, you could. Yeah, absolutely. Yeah, if you took the warm jug of water, put it in the fridge, it's going to lose entropy more quickly than the cold one. Yeah, because it's further from equilibrium.
So is it losing entropy more quickly? Would it have more entropy?
Well, the fact is the fridge is going to work harder, and so more heat's going to spray out the back of the fridge. Yeah, and when your power bill, your meter's going to spin faster,
Yeah.
and more coal's going to fly into Colstrip. So it's around and around we go, right? Or more demand's going to come from the solar panel, or more is going to come out of your battery, or more is going to, wherever you're getting energy from. Yeah. That is exactly how to think about it. So that's entropy. And here's that 500 exajoules per year. We saw that in chapter 1 or 2 of our text. I then went in and said, well, what's the volume of the Earth's atmosphere? And what's the volume of the universe? And I just said, like, on a per volume basis, it's just back to your jug of water. Your little jug of water in the fridge could be just like the Earth inside the universe, and the entire Earth. Just think of all these other jugs of water that people are cooling off in their fridges around the planet. That could be the universe. Yeah. So you can scale this up or scale it down. It's a good segue. And so what I say here is that with our technologies, we entropicize our environment 10 to the 23rd times faster than if we weren't setting things on fire. If there were no technology. So you remember back to that 200 watts per person. That's what that adds up to. And
What is the background entropy generation rate of the universe? I thought they
yeah. So what
Cooling.
what I tried to do with the background rate. I'll just show you there. Okay, so to find the entropy generation of the sun, we divide the sun's radiant power, so it's 383 yoctowatts, which is 10 to the 20, I think it's 10 to the 24th, because I think 10 to the 18th is exa, 10 to the 21st is zeta, 10 to the 24th is yoctowatts. And there's its temperature, 5,600 Kelvin, and so that's the sun's entropy generation. So it's just the power divided by temperature. There's its entropy. Now, I just said the sun's an average star, and this, at the time I wrote this, there were an estimated 10 to the 22nd stars in the known universe. Wikipedia did. Then divide it by the average temperature of the universe. Pretty cold. That's the average temperature. I came up with this. This is, so 8.4 times 10 to the 48th watts per Kelvin. And then somewhere there was the universe has a known volume too. And so this is the background on a per volumetric basis. So you can think of that as the one the one jug of water and the one fridge. Or, I'm sorry, you can think of this as all of the jugs of water and all of the fridges, just, stars sort of spraying their light off into the universe versus, our little planet here. Yeah. Okay. So that's the entropy side of things. And now let me show you. So there that is. And this is Boltzmann's constant. Boltzmann's constant is actually in joules per Kelvin. It's joules per Kelvin. And these are just probabilities. These are just the probabilities of finding something in a state, in one state versus another one. So if we just went and, if you want to take a look, there's this thing called Maxwell's Demon. It's kind of cool. Maxwell was a contemporary of Carnot too, but it just says that if I have a box of molecules, as the temperature goes up, the average velocity also goes up. But it could be that bouncing around, so you've got a bunch of little molecules heading off in different directions. It could be that one particular molecule at any given time is just standing still. So think about a billiard table. It could be just as two balls are colliding, one just stops. But that means that it gave another one more energy exactly. So the average energy is all still there, but the point is there's a certain probability of finding one of the little particles not moving. So that's the microscopic definition of entropy. Okay, and then I just show that temperature itself is just energy per particle. That's very well known. Nothing really new. So all of this is just kind of churning through that. There's a paper too. If you take 102, we'll read this paper by Solomon, and Solomon actually looks at the change in global thermal energy, and they actually do it with they actually look at entropy without even kind of knowing it, which is kind of cool. And then okay, and then this is, so if you look, this is Shannon information. So it looks almost identical, except there's no constant out in front. There's no Boltzmann's constant. So the units of Shannon information is just bits. And the easiest way to describe it, if you look at this guy, this is the power in a signal, and this is the noise. So, everybody's driven their car, and, the more powerful a radio signal is, the further out of town you can hear it, right? If they've got a bigger antenna, P, it just means that the communication channel is better. If there's more noise, that number gets bigger, so this thing gets smaller, and now you got a bunch of static and you can't hear it. This was Shannon. So as it turns out, the information in a given signal is a function of the probability of a certain word coming through next and how frequently it occurs. So if I just sat up here and went like, you're like, oh, not very interesting. There's no information being conveyed. Or if I just sat up here and just like, like just very monotone, like, got it, nothing. So the information content in the signal is based on the unpredictability of what's coming out. So the more this is why I hope if I have a broader vocabulary, it's more interesting. There's more to it. Or if you listen to a more complex song, at some point it becomes too complex. It's like, so there's a sweet spot there, and so that's information. What I tried to do with this paper is just show that there are certain technologies, like the Google car, that are doing both. They are pulling in information, We use it all the time, but they're also generating entropy. So I think somewhere down here.
Didn't Google car get pulled over for going too slow down in California?
Might have.
I think that's what happened. It was like doing one of those little test runs or whatever.
Yeah.
And it just was going too slow and impeding traffic.
Yeah.
The cop
Except for the
pulled
cop.
over the car. Yeah, the cop pulled the car over, or tried to, but then it saw no one in it.
Oh, really?
It was like, what the,
Not surprised. So what I tried to do with this little equation is show that if there's a given technology that is processing a lot of information without generating much entropy, it's preferable. It's the same thing with your, so just think about your own computer, and this is a good story. So one of my colleagues was up in Nome, Alaska, and he was trying to calculate wind loads on this big wind turbine. But the battery in his laptop had died. So, if his battery were working, he would have just been running at a very low entropy rate. He would have been running at 90 watts divided by whatever the temperature was, 250 Kelvin. But his battery was dead, and the only energy source they had was this 25 kilowatt gasifier. So they, so they had to fire up this 25 kilowatt machine just to get his little laptop going so he could build the wind farm. But the point is, in both cases, all they wanted was the information out of the laptop. All they wanted was, where do I put the wind turbine, how thick is the metal, et cetera, et cetera. They just wanted to know, what's the plan for actually pulling this thing off. So if the battery had been working, the what did I call it here? The informational fitness of the machine would have been better. And it's the same way, let's just say you're sitting down and trying to study for your exam or take your exam. If the room is too cold, your body is spending a lot of energy keeping your brain at the right temperature. If the room's too hot, it's the same thing. Your body is metabolizing all of this energy to keep your brain at the same temperature. So you can also imagine your own neural computer in your head as having some informational fitness. So the point of doing this is that we should get to a point where we're running our laptops on batteries instead of 25 kilowatt generators. It's just more fit. And you can do the same thing for any car. The whole point of getting your car and going somewhere is have an experience. Maybe get some energy. Maybe go to a movie. But if you're burning through all these resources to do it, you're not as fit. So that's the whole point of the paper. Okay. And the
All comes down to a balance.
a little, yeah. And so the curveball I throw in there is, bits per second. This information is measured in bits. So bits per second divided by watts per Kelvin. So as it turns out, we can have a informational fitness of the Google car, and this number won't make a lot of sense unless you compare it to something else. But I think I don't know. So read through it and say, gosh, what are these? How do these numbers compare? If I put a and I also tried to show how our information processing has changed dramatically over time. There's a little, you were asking earlier, Tyler, about the how you would get to at the celestial scale. This just shows two stars shining at each other. So this is a relatively new way of thinking of it. Again, we can blame Richard Feynman because he threw that out there 60 years ago or so, but never really followed up on it. So I thought, what the heck, I'll give it a shot. So, all right, let's just pause there, and then I will look at. So now we've covered summary 5, and now let's look at chapter 13.